In a world defined by motion and control, where every component matters, a new standard emerges. Mech-Vengers.
We are Mech-Vengers, and this is our V6 race engine project. In this presentation, we'll walk you through our design process, how the engine works, and the engineering analysis behind it. In racing, performance is everything, and that's exactly what drove this project. Our goal was to design a V6 engine that could handle extreme conditions while still maintaining power, efficiency, and control. Every component in this design was carefully selected and engineered with a purpose, not just to function, but to perform under pressure when it matters most. Before choosing the V6 engine, we explored several other concepts, including a jet engine, a mechanical iris, a planetary gear system, and a robotic arm. Each option had its own challenges. But we ultimately selected the V6 engine because of its versatility. Even though it's a familiar system, gave us the opportunity to better understand mechanical motion, refine our design skills, and demonstrate stronger engineering knowledge.
Behold, innovation to reality.
The V6 engine works by converting chemical energy from fuel into mechanical energy. Air and fuel enter the cylinders, where they are compressed and ignited to create combustion. This combustion generates force that pushes the pistons downward. That linear motion is then transferred through the connecting rods to the crankshaft, which converts it into rotational motion, producing the power needed for engine performance. The engine is made up of multiple sub-assemblies that all work together as one system. These include pistons, the crankshaft, connecting rods, rocker arms, camshaft, valves, intake and exhaust manifolds, as well as the engine block and cylinder head. Each component has a specific role, whether it's generating power, controlling timing, or managing airflow, and together they ensure smooth and efficient engine operation. We focused on three key components. The piston converts combustion into linear motion and is made from 7075T6 aluminum for strength and low weight. The crankshaft converts that motion into rotation using AC 4130 steel for durability. The rocker arm controls valve timing and is also made from 7075T6 aluminum for efficiency. After designing the components, we moved on to the assembly process. We followed a structured approach, starting with the base components and gradually adding smaller and more complex parts. To ensure realistic motion, we applied mechanical mates, including cam mates, which allowed us to simulate how the engine would behave in real life. For our stress analysis, we focused on the crankshaft. This is because it's the central component for power, transmission, and experience is the highest. Torque and repeated loading, since it plays a critical role in performance and reliability. It was the most important component to evaluate. The results of our analysis gave us important insights. The maximum von Mises stress recorded was approximately 5.657 times 10 to the power of 7 pascals, or about 56.6 megapascals. This stress is highest in areas like the crankshaft fillets, where geometry causes stress concentration. We also measured displacement. which was around 1.4 to 1 times 10 to the power of negative 2, a very small value. This indicates that the crankshaft remains stiff and does not significantly deform under load. Overall, these results confirm that the design is structurally sound and operates within safe limits. Thank you for your attention, and remember, we're assembling innovation one part at a time.